Can you see my screen now?
Yes.
Can see on my screen, right?
Yes. No.
Because I won't be able to see you all. Okay, I can only hear your voice when it comes to this. Okay, so can you see this screen, everyone?
Yes.
Yes.
Can you see my laser pointer, the red dots? Everyone can see
Yes.
the red dots?
Yes.
Wait. Now, this is the laser pointer, yeah? This, okay, goes with the laser pointer. Okay. Now, mechanics of engineering materials, yeah? Mechanics of
So have you
engineering
recorded?
materials. Pardon?
Have
Yes.
you recorded?
Yes.
All right.
Yes. Okay, thank you. Now, the first chapter we are looking at is on stress and strain. Stress and strain. Okay. Now, the main objective of the study of these mechanics of materials is to provide the future engineer with the means of analyzing and designing various machines, various parts of machines, of various machine components, and load and structures. Structures means buildings, bridges, and all those, yeah? Can you see chapter objective, everyone? Chapter objectives. Now, first thing is static. Now, you still remember what it means by static or not? Now, this is a branch of mechanics which concern with bodies or most like particles, bodies or components which is at rest. At rest, that means not moving. If it is moving, it must be moving at uniform speed or uniform velocity. Then only we can do the analyzing of the stress and the strain. Okay, so we have to take the object to be at rest first. Then only we can do the analyze of stress, strain, and loads on the object. Okay, and of course, the forces must be in equilibrium. Okay, equilibrium means state of balance, yeah, state of balance. Now, in this chapter, we will review some of the important principles of statics. Okay, I've explained to you what it means by static and show how they are used to determine the internal resulting loadings in a body. Now, everyone knows that, okay, Newton's third law is dealing with every action, and that should be having an equal and opposite reactions, right? So the resultant loading that is acting on a body, that's very important, yeah? So we are looking at the level of the molecular structure. Now afterwards, after that, the concept of normal and shear stress, normal stress and shear stress. Okay, later on, I will explain to you what is normal stress and what is shear stress. That will be introduced, and the specific applications of the analysis and the design of members is subjected to axial load or direct shear will be discussed. Now, first thing, mechanics of materials. Now, it is a branch of mechanics that studies the internal effect of stress. Okay, no one is stress. Stress in general is defined as force over area. Stress in general is defined as force over area. So we will be looking at, or we will be making a studies on internal effect of stresses and strain in a body that is subjected to external force or external loading. So forces that is acting, okay, externally outside, okay, of an object. So when there is an external force acting on an object, okay, there should be an internal resistance. That means should be a reaction towards the external force that is acting on the object. Okay. Now, without diagrams, I know most of you don't understand what I say. Okay, later on. Okay. Now, stress is associated with the strength of material from which a body is made. From which a body is made. The materials which the component or the object is made of. So we are looking at how much of strength or how much of resistance or how much of ability that the object can withstand when you have forces acting on it. That is called strength of material. Or in other words, strength of material is actually the mechanics of materials. Now, so here I have the definition of strength of materials. So ability of the materials to withstand any external load or force without failure. Okay? Clear, everyone? Everyone hear me? Okay,
Yes.
good. Good. While strain is the measure of the deformation of the body. Deformation means, if let's say, for example, you have a rod, R-O-D, rod. Okay, you have force acting on the rod. That means you have force pulling, just like a rubber band. When you pull it, rubber band, everyone knows what is a rubber band, right? So when you have force acting on the rubber band, when you exert a pulling force, what happens to the rubber band is it elongates. It elongates. That means the length will increase. So this increase in length of the body, that means of the rubber band, is called deformation. Deformation. Or if let's say, for example, when you refer to a plastic ruler, and then you apply force from your finger, by your finger, press the ruler down. So the ruler initially is horizontally straight. So when you apply a force through your fingers on top of the ruler, push it down. So what happens is the ruler will bend. So that is also called a deformation. The next thing, when you refer to a spring, everyone know what is a spring, right? So when you apply external force, that means when you pull the spring will expand, okay, will increase in length. So the increase in length or the extension is called deformation also. Okay, or if let's say you apply two pushing force, pushing the spring together, compressing it, the spring will be shortened. So the changes in length is called deformation also. Okay. So in addition to this, mechanics of materials includes the study of the body's stability, how stable it is without failure. Okay, when a body such as a column, okay, I've explained to you what is a beam and what is a column, okay, is subjected to compressive loading. So this is all about mechanics of materials. Or previously, let's say 10 years ago, we called it, this subject, we called it as strength of materials. But nowadays, we call it as mechanics of engineering materials or mechanics of materials. Now, this subject usually, what are the type of engineering students will be doing this subject? Mechanical engineering students, because they will be dealing with the design of machine parts, machine components, and so on. Civil, architecture, and QS students also will be doing this subject, but then they are dealing with, okay, especially civil, they will look at the ability of structures like beams, columns, bridge, buildings, the joints, how much of stress, how much of load they can withstand. Okay, that is for civil students. For architecture and for QS students, they will look into the type of materials that is suitable for the use of that such application. Okay, so that is this is usually studied by mechanical engineers, civil engineering students, okay, architects. load. What is external load? A body is subjected, that means an object, okay, is subjected to only two types of force, two types of external loads. You all know what are forces, right? Anyone don't know what is a force?
What, sir?
You all know what is forces, right?
Yes.
Okay, so when you use your hand to push a table, that means you are applying a force in pushing the table. So if there are ton of forces, there are a lot of forces acting in from all directions. And if you add up all this external force that is acting on the table, we can call it as a load. If let's say, for example, you have your dining table, and then you go and stand or you sit on top of your dining table, you are actually exerting a load or a force, a load, okay, on the table. Or when you sit on a chair, okay, when you sit on a chair, your whole body is actually exerting a load or a force on the chair, okay. So the legs of the chairs, where you have the joints between the seat and the leg, okay, will be subjected to forces due to your body weight, due to your body weight. So your body weight is one of the external load, okay. So external load can be, okay, categorized as two, okay, forms. One is called the surface force or the surface forces, and the body forces. Surface forces and the body forces. Okay, what is load? Now you see, I'll give you the definition of load here. Load, it is defined as any external force acting upon a machine part or a component, not necessarily a machine part, a structural part also can. Surface forces, what is surface forces? Now I will explain to you. Now surface forces are caused by direct contact. What is direct contact, right? Of one body with the surface of another. So let's say, for example, just imagine you have two objects, you place it together, close to each other or touching each other. Or let's say, for example, okay, you have a plate of dishes or a bowl of soup, a bowl of soup. You place it on the table. So you have two objects touching each other. That means the surface of the bowl of soup is touching the surface of your table. Then hold on for a while. Hold on for a while. Okay, so surface forces are caused by the direct contact of one body with the surface of contact, direct contact of one body with the surface of another. Now, in all cases, these forces are distributed over the area of the contact between the bodies. Just like, for example, you have a bowl of soup. Okay, you place it on top of the table. So the weight of the object or the weight or the forces from the bowl, that means that because the bowl itself has a weight, and then you have soup inside of it. So the forces, okay, the forces or the weight will be all equally distributed onto the surface of the table, Okay. Now, when I read out this, I know I have to draw diagrams for you all, okay? But then, unfortunately, I can't do it now, okay? But then I will show you the diagrams afterward. Now, if this area is small in comparison with the total surface area of the body, then the surface force can be idealized as a single concentrated force. That means, let's say, for example, the bowl of soup, okay, is in contact with the surface of the table. If let's say you reduce the surface of the table, minimizing, you just imagine you are going to reduce the surface of the table, becoming smaller and smaller and smaller. So the bowl of soup that is acting on the table now seems like it's acting on a point. It's acting on a point. So this type of force, we call it as concentrated force. Usually concentrated force, okay, in diagrams or in free body diagrams that we are going to draw, is usually represented by using or drawing an arrow pointing at a particular line or surface. So we usually call them as concentrated force. Point load, or we call it as point load, or we call it as concentrated force, which is applied to a point on the body. This is the surface forces. The next one is body forces. Now, in general, because I won't be reading up the whole thing again. Now, the body forces here usually refers to WEIGHT, the weight of the body. Now, these body forces usually is due to gravitational attraction. And this body force not necessarily has to be in contact with something else. Okay, it might be it might be at a distance away from the object that it is acting on. So this force is called the wave. Wave, WEIGHT, is usually due to the gravitational attraction. Okay, gravitational attraction from the center of the earth. Now, everyone okay? Everyone still around or sleeping already?
Okay, sir.
So wave is given as, what is the formula that we use for wave? mg. Okay, mg. Okay, so I won't be going too much on this type of, okay, writings. Too much already. Now, stress. Now, when some external system of force or load acts on a body, the internal forces, which is equal and opposite, are set up at various sections of a body, which resist the external forces. This internal force per unit area at any section of the body is known as stress. Stress. So in general, stress is defined as force over area. Hold on. Hold on, yeah. Yeah. Okay, now hold on, because I'm picking up something from poster. You want to take the rest for 5 minutes? Okay, I'm back. You all still here?
Yes, still here, sir.
Okay, thank
Yes.
you. Thank you. Now, stress is defined as force over area. If let's say, for example, you all don't want to look into so much of wordings and all those things, just remember stress, the symbol that we use is sigma, is equals to force over area. Okay? So mathematically is written as stress, sigma is equals to force. The P is the symbol that we use for force, not pressure here. Force, or you can use the uppercase letter F, that means the big F, force, over area. A stands for area. Remember, we deal with this stress. This is called, okay, stress or direct stress. Direct stress. Okay, direct stress. And usually for direct stress, this stress, the force and the area, they have to be 90 degrees to each other. 90 degree to each other. Just like the diagram that I show you here. I'm going to show you here. So this is the force. So usually it's represented by an arrow like that. Okay, so we call this as a concentrated load or a concentrated force that we have said just now. Okay, concentrated force or concentrated load. So it can be shown as an arrow in this form. And then make sure when you deal with this stress here, sigma, stress. Now you all know generally what is stress when you refers to human beings, right? Now, I think most of you got a lot of stresses now due to MCO period, where you are not allowed to go out and so on, right? You say, I am stressed because I'm not able to go out, do shopping, go for movies and all those things, right? So we call those as stresses for human beings. For objects or components, when we say stress, is when you have force acting on the surface or acting on a particular object. So let's say, for example, you say, okay, I give you a lot of homework. I give you a lot of homework. That means you have a lot of force. You have a lot of things to do. You have to do a lot of things to remember. So you are subjected to heavy load. Heavy load, that means a lot of workload. Workload, that means you have to do your homework. You have to study this. You have to study that. You have to get ready of your lab reports and everything. That is load. When you are subjected to too much of load, you say, okay, physically or mentally, you say, I am subjected to a lot of stress. But when you refer to objects or components, okay, the stress is only when there are forces acting on it. And the area that is in contact with the force has to be, now, you look at my pointer, yeah? Now, this line here, can you see this dashed line here? Look at my laser pointer. This line here is called the line of action of force. Line of action of force. So, and then this is the surface area. This plane here is considered as the surface area. So when you look at the force and this plane here, is it 90 degree? Is it perpendicular? Yes. So whenever you consider the stress, the area that you consider must be 90 degree to the force. So we take this force here divided by this area here, this whole thing here, this area here. It will give you what we call the direct stress or the stress. Any problem? Everyone, any question?
No.
Okay. So for direct stress, the area of contact must be perpendicular or 90 degree to the line of action of the force. So that is how you see it. So that is where the force is acting on the surface of the object. So remember this area here and the force must be always 90 degree when you're dealing with what we call direct stress. What we call direct stress. Everyone okay? So
Okay.
now these are a few
Okay.
more examples. Yeah, thank you. Now these are another two more examples. You can call these as columns, cylindrical columns, or cylindrical bar. Why we can call it as columns? Whenever you put something with length like this and place it vertically like that, is called columns. You can call them as columns, or you can call them as tie. Tie is when tie, tie. That is your the same word that you use for your necktie. Tie is when the object is subjected to pulling force like this. Pulling force like this. So we call this as tie. And we call this as column when you can see both of the force that is acting on the object is compressive. This is tensile, pulling, and this is pushing. So we can call this as column, we can call this as tie, T-I-E. Okay, when it is subjected to tensile, we call tie, T-I-E. When it's subjected to compressive, we call it as column. Okay, so remember, if I want to find the stress that is acting on the object, like this, the area should be this area here. Everyone clear? So this area here should be the circular cross-sectional area. What is the area of a circular cross-section? Pi r square. R represents radius, or you can use pi d square over 4. D refers to diameter. So this is compressive and this is tensile. So what happens when the column is, or when the bar is subjected to compressive force like that, and when the bar is subjected to pulling force or tensile force like that? So due to compressive force, you see it will shorten. Due to pulling force, the thing will expand, elongate. We use the word expansion or elongation or increase in length. Okay, when it is subjected to compressive force, the object, we say it is being shortened, shortening, or we can use the compressive word, compressed, or decrease in length. Follow? Tensile and compressive. Now, you can look at these examples also. Now, all these are called point loads or concentrated loads. Concentrated loads, okay? So here we have springs. When they are subjected to tensile force, pulling. So what happens is the springs will tend to extend. So the springs will tend to extend and compress and extend and compress because springs are elastic materials. So when it is subjected to forces, it will again deform. We use the word deform, deformation. Deformation can be referring to shortening or contraction, elongation or extension or increase in length. Okay, all this we call it as deformation. Now, every material is elastic in nature. Every material is elastic in nature. So whenever some external system of forces act on a body, it will undergo certain amount of deformation. Okay, as the body undergoes deformations, its molecular or its molecules or particles that is within the object set up some resistance towards deformation because the object is in a regular shape or in a regular form. When you have forces acting on it, what happens is the force will cause the object to deform, to change in shape, to change in length, to change in diameter, to change in width, to change in its thickness. But the object wanted to remain as its original form. So therefore, what happens is the object itself will induce, that means produce internally, will induce an internal resistance towards the external applied force. So this internal resistance that the object induced, okay, over the area will give you what we call stress. Okay, so simply we say force over area give us stress. Okay, everyone? Now, what is strain? When a system of forces or loads acts on a body, it undergoes some deformation, just like the diagram that I've shown you just now, all the diagrams. When the object is subjected to pulling force, it will undergo extension, elongation. Okay, when it's subjected to compressive force, it will undergo contraction or shortening. Okay, so the shortening and the elongations, or either elongations, they are called deformation. Deform, that means changes in length, changes in shape, changes in thickness, changes in width, and so on. Now, this deformation per unit length is known as unit strain, or is called strain. So if, let's say, for example, we take deformation over the original length, that means if, let's say, the object is subjected to pulling force, it will undergo elongation. So the extension or the elongation divided by original length of the object will give you what is called strain. Okay, so Greek letter, we use this symbol here to represent strain. This symbol here is known as epsilon. In Greek, it's called epsilon, and this represents strain. Strain. Okay, mathematically, you can write that as strain is equals to changes in length. Delta here means change. L, that is length, changes in length over or divided by original length. Or you can manipulate this equation here so that you can find the change in length by taking the direct strain times original length. Okay, so where delta L, that means the change in length, okay, represents the change in length, and L represents the original length. Okay, here I got examples. Now, so basically when you refer to this bar or this rod here, when it is subjected to pulling force like that, you can see that this rod here or this bar becomes thinner, thinner, T-H-I-N-N-E-R, thinner, and longer when it is being pulled, becoming thinner and longer. So when you look at these edges here, actually the object here has undergoes a deformation. That means increase in length. So that gives you the final length after the force is being applied, where this is the original length. This is the final length, which you take original length plus the changes in length. These are the changes in length here, and here is called the changes in length. So if you take the change in length here divided by its original length, you've got what is called the strain here. Okay, so and if let's say compressive force, if let's say this is the original length of the object, if this is the original form of the object, if you apply compressive force like this, compressive force, what happens is the object will undergo shortening. Shortening, that means become shorter. So that also will give you the deformation, the changes in length. So these changes in length over original length will give you what we call strain. So this will be the original length, and this will be the final length here. Because why you minus? Because it has undergo shortening. Okay, that is strain. Okay, now any questions? Anyone have any questions? What is the time now? Okay, we still have 30 minutes. Any problem? Class, you are still there?
Yes.
Yes, sir.
Yes. Yes.
Yes, you're here.
Okay, thank you. Now, the next part, okay, we have two more pages, two more slides to go, then we finish this part. Okay, shearing stress. Now, shearing stress is due to, okay, when a force, okay, when there are two forces, that means sliding force, tangential force. It's just like, for example, you just imagine that you are shuffling a pack of playing cards where you used to gamble, judi one. Okay, you shuffle. Okay, so when you shuffle, your palm, both your hands, your palm is touching, one of your hand is touching on top of the first cut, yes or no? The surface layer of the first cut. And then the other hand of yours is touching on the bottom surface of the bottom layer of the cut. So how to shuffle? You have to move your hand, both your hand or both your palm, your hand in the opposite direction, correct? So when you move your hand, both your hand into opposite direction, what happens is actually you can see the cuts are sliding over each other. So we say the pack of cut is undergoing shearing. Shearing. Follow? So shearing is usually caused by these forces. That means your top hand and your bottom, the hand that is on top of the cut and the hand that is at the bottom of your cut, which is moving in the opposite direction. We call that forces acting in. That means these forces exerted by your hand is called tangential force. They are called tangential force. Okay? So it's the force per unit area that causes the layers or parts to slide upon each other in opposite direction. Okay? The force or the stress, okay, the force per unit area, which is the stress that causes the layers or the parts to slide upon each other in opposite direction. Now, shear stress is also defined as force over area. Shear stress is also defined as force over area. So F over A, but the force here, we called it as the tangential force or the shearing force. And the area, there is a difference between the area due to shear stress and the area of the direct stress. Now, previously, the area that we consider must be 90 degrees to the line of action of the force. The area must be 90 degrees to the line of action of the force. That is sigma. Previously, the one sigma, that is the direct stress. Now, for shearing stress, the area must be adjacent. That means parallel, adjacent or parallel to the direction of or to the line of action of the force. So just like, for example, you just imagine a pack of cards, you have your hands on top, you have your hands at the bottom. So when you move both your hands, okay, in the opposite direction, you are causing sliding. So the area that you measure, okay, must be the total surface area on top of your hand. So we say the area is actually being adjacent to the direction of or the line of action of the force, being adjacent or being parallel to the line of action of the force. Okay, so I give you a diagram. Now you can see how the things, okay, slides over each other. You can see these forces here, we call them as the tangential force. The area, how we consider the area? The area is the area here. Okay, the rectangular surface area, okay, of the object. So you can see this area here is actually adjacent or parallel to the line of action of the force. This is the force. The area that you consider the green one, the green shaded part. Okay, so that is the area. So the area that you consider for shear stress and the area that you consider for direct stress are different. For direct stress, the area have to be 90 degrees. For shear stress, the area have to be parallel or adjacent to the direction of action of the force. Okay, so these are the areas that you have to consider. This rectangular, okay, section here. So this area here. So these are called the tangential force. They are moving in opposite direction. Okay. So line of action of the force being adjacent or parallel to the contact area. So make sure the line of action of force and the area is parallel. For direct stress is 90 degrees. Okay, so to measure the shear strain, the strain that we have just now, epsilon, is called the direct strain. Okay, so in this part here, we will be dealing with shear strain, and we give it a symbol of, okay, gamma. Shear strain is defined as also deformation over original line. But then the deformation and the length here, they are 90 degrees to each other. Deformation and the length are 90 degrees. But when you refer to stress, the area and the force is parallel. But when you refer to deformation or when you refer to the shear strain, the deformation and the original length here is 90 degrees. So that is the difference between direct stress and shearing stress, direct strain and shearing strain. Okay? So internal forces, in all cases mentioned earlier, the internal force can be indicated by a single arrow. In fact, for each section to be in balance, there must be an internal force in the opposite direction. This leads to the standard convention of the indicating the type of stress on the diagrams. So here I've got 3 diagrams. Now the first one you can see. Now the blue arrow here tends to pull, if this is an object, tends to pull it outwards, elongate. But then the internal resistance, you see, the red arrow represents the internal resistance. The blue arrow represents the external applied force. External applied force, the blue arrow. The red arrows is called the internal resistance. You can see they are in opposite direction when you refer to this pair, the blue and the red, and this pair, the blue and the red, they are actually acting in opposite direction. But their size of the force, that means if this is 5 Newton, this has to be 5 Newton now, of course. This is 5 Newton, this is 5 Newton, and this also must be the same. If this is 5 Newton, this must be 5 Newton. And this diagram here represents tensile pulling. This diagram here represents compressive. You can see both the blue arrow here is actually moving forward. Okay, these 2 blue arrows here is moving away. These 2 blue arrow here is moving towards. So this is compressive. And the red arrows shows the internal resistance. Okay, so the external applied force, the blue arrow, is actually pointing towards each other. But the internal resistivity or the internal resistance is actually acting away. So this set of, or this diagram or this set of arrows or this diagram here represents compressive. And this represents shear, where you can see these 2 forces actually they are sliding over each other in an opposite direction. Shear, compress, and tensile. For any tensile force or tensile stress, by nature, we consider as positive. For compressive, by nature, we consider as negative. Okay? Now, there are some important points that you need to know here. The equations of equilibrium. You all know what is equilibrium. I hope you all still remember what is equilibrium or a state of balance. Okay, for equilibrium, when you work out equations on equilibrium, make sure there are 2 conditions you have to follow. The first one is the total sum of forces must be equals to 0. The second one is the total or the sum of moments must be 0. In order to keep an object in static, that means not moving. Okay, even though if it is moving, it must move at uniform speed so that there shouldn't be any acceleration. When you do this subject or when you do static, it is always advisable that you cannot consider the object to be having any changes in speed or any acceleration. So that means static. Remember, to solve any problems in strength of material or in mechanics of engineering materials, you always make use of these 2 conditions here, these 2 equations or conditions here. That is the total force equals to 0 and the sum of moments equals to 0. When you say total force or the sum of forces equals to 0 means what? When you take the total force acting towards the left and the total force acting towards the right, it must always give you a 0. Or even though if you take moment, the total clockwise moment with the total anti-clockwise moment always must give you a net moment as 0 and a net force as 0. Okay, when applying the equations of equilibrium, it is important to first draw free body diagrams. I hope you all know what is free body diagram by now. You have done static, you have done dynamics, if I'm not mistaken. Okay, and then the sign conventions, tensile to be positive and compressive to be negative. Okay, everyone? Still around?
Yes, still around.
Okay.